Yeah, okay, I think we can start. So, hello everybody. This is Luboš Pirkl and Radek Máca from CFD Support. Welcome to the webinar on Turbomachinery CFD, which is a CFD simulation workflow for all standard rotating machinery. Just in case of any technical problems, feel free to contact us in the future and we will gladly answer all your questions and reminders. The test case for today is compressor. So we will show you, or we will show you how to run compressor, how to simulate it, how to evaluate the results. So please let me introduce us a little bit. So this is me. My name is Luboš Pirkl. I am co-founder and managing director of CFD Support. And today I am sitting here with my colleague Radek Máca. Hello, Radek.
Hello everybody.
So Radek, how are you today?
Yeah, Luboš, thank you for asking. I'm fine today and I'm looking forward for this webinar.
Okay, so are you ready? Can we go?
Yeah, I am. You can continue.
Okay, so I will just say a little bit. Radek is our head engineer and senior developer here at CFD Support, and he will take care of the technical part of today's webinar. So I think, yeah, so let's go. So I will switch the camera off, and yeah, so the webinar is going to take about 1 hour, depending on the number of your questions and reminders. There will be 3 parts in this webinar. In the first part, I will give a general introduction to Turbomachinery CFD. I'm gonna point out the main Turbomachinery CFD features and benefits. In the second part, Radek is going to show you how to simulate a compressor in Turbomachinery CFD. And in the last part, there will be a Q&A session dedicated to your questions and our answers. Feel free to put your questions. There is a special window where you can put your questions, or you can even send us your questions to info@cfdsupport.com and we will answer them later in this webinar. And for your information, especially in the beginning of this webinar, we are going to be quite general, but feel free to ask about the details and we will gladly provide all the information. So we are prepared, we are ready to tell you everything we can and we know. So CFD Support, about the CFD Support. So CFD Support is the private engineering company dealing mainly with computational fluid dynamics. We are used to deliver complete consultancy projects, open from support, open from research and development. We also deliver open from trainings, and of course our flagship product is Turbomachinery CFD. Let me give a brief description what Turbomachinery CFD is. So Turbomachinery CFD is a unique software based on OpenFOAM, and it was designed for CFD simulations of all rotating machinery, such as pumps, compressors, fans, turbines, water turbines, both radial and axial machines, both compressible and incompressible fluid flows. It's complete. Turbomachinery CFD is complete, so it covers all the engineering steps from the pre-processing over the simulation run to the very detailed post-processing of the results. So it's independent on any other software. It's comprehensive. Let me put just a quick review of its unique value proposal. So we believe Turbomachinery CFD is unique at least for 4 reasons. Number 1 is Turbomachinery CFD has no licensing policy, which means our clients can keep Turbomachinery CFD forever and they can use it for unlimited number of users, jobs or cores, and that gives their investment in Turbomachinery CFD a permanent value. Number 2 is Turbomachinery CFD is fully automated, which means all the workflow from the initial data to the final engineering results can be run by a single click or by a single command, and all the process is being done automatically. And for this reason, Turbomachinery CFD is extremely effective. Number 3 is we deliver extraordinary technical support we are proud of. We keep custom approach to every customer, to every issue, and we are very flexible. We never leave behind any issue of any of our customers or clients. We support our clients even in matters out of the Turbomachinery branch, like in mathematics, physics, CFD, IT, or even software engineering. And number 4 would be the real tutorials are included. So Turbomachinery CFD has, the user has no doubts about the best practice settings. The real machines that are already preset are included. So basically you can take one of those machines, one of tutorials, and basically you can just replace the geometry or the model with your own, and you can just modify the physics, modify the settings, and run the simulation. So it's prepared, and it's already prepared to start your own simulations. There are many other benefits of using Turbomachinery CFD. I'm not gonna go for all of them. I will mention some important technical details. So Turbomachinery CFD is available both for Linux and Windows operation system. And by the way, in today's webinar, we will work from the Windows operation system. The Linux workflow is very the same as in Windows, so it's always your choice which operation system to choose. Turbomachinery CFD workflow is fully served from a graphical interface, from a GUI. The graphical interface for Turbomachinery CFD is the ParaView. You can also work from terminal, but the most people prefer to work from a graphical interface. Of course, Turbomachinery CFD can be also run on clusters or clouds to scale your CFD simulations in a really big way. The decision is always up to you, up to our clients. The workflow can be scripted in Python. Turbomachinery CFD is very transparent. The trial version is available for free for 1 month period, so anybody can try it, and afterward he or she can decide to go for it or not. Real tutorials are available, and also every single simulation has its detailed results report in a web responsive HTML format or even in PDF format. So every single simulation has its PDF report. The part of Turbomachinery CFD is also TurboBlade Post, which is a special package for really detailed visual post-processing of Turbomachinery CFD results. And finally, Turbomachinery CFD includes a CFD processor, which is a special software for automating tool of OpenFOAM cases. And finally, perhaps the most important information of today's webinar is all the information is available online. So you can go to visit our website of Turbomachinery CFD, and you can get information from there. I think the first part is over, and now it's time to come back to Radek with a live example. So Radek, are you ready for your part of the presentation?
Yes, I am, Luboš. Thank you. So you can make me a presenter.
Okay, with pleasure, Radek, with pleasure. So okay. I need to do, I will make you an organizer, which I did right now. So I hope you are now, did I?
Oh yeah, now I see, and I believe you see my screen now.
Yes,
perfect, yes. Perfect. Okay. So thank you, Luboš. Thank
you,
Luboš. And I will directly start with the technical part. So I'm going to show you right now how to run a tutorial case in our DCFD software. So today's tutorial case is a compressor. So what you need to do to start using our software consists of two simple steps. So first step is to go to our web pages, go to our product page, Turbomachinery CFD, and here you can click by clicking on it and fill this form. You can ask for a trial version. So if you will just apply, and we will send you a full version which you can use for 1 month for free. And after you downloaded it, you simply install it. The installation process is really simple, and afterwards you can directly use our software. So today's case is a compressor case, and you can jump to the download section. Here, the first item is download cases, and in this list you easily find the radial compressor case. So just click on it, fill this form by just let us your email here and click to download the case. So I will provide my email address, click on download, and the download process starts. So I have already downloaded a few minutes ago, so I will start directly to using it. Well, so to start using our CFD software, there are many options. So first you can use any file browser you are familiar with. So for example, I will use implicit Windows file browser. I will jump to the OpenFOAM directory, to my 16.10 version, to my home directory, and here I have downloaded the radial compressor case. So the starting point is only the geometry in STL format and the TCFD file, so the source file in which you define some parameters which is needed to run the case. So I will go through all these steps. So the STL geometry consists of several parts. You can check it, for example, in ParaView. I have made an association with ParaView, so if you don't have, so just run OpenFOAM by clicking on the icon on your desktop and by typing ParaView. Yeah. So the ParaView will be opened, and you can find this STL files in radial compressor, STL, and I for example open just the rotor part, and this is the input for our software. So using this geometry, the computational mesh will be defined. So at the beginning you just need the STL geometry and the configuration file. So it is a simple file, so I will open it in the notepad, and it is a simple file with few parameters to define, and this parameter defines all case. So first option is to manually define the parameters inside this text file, or you can use directly the graphical user interface. So just by clicking on this TCFD file, the ParaView will be opened, and directly in this left panel you see the all parameters which is defined for this particular case. So I will briefly go through all these parameters. Okay, in this way I will move, for example, here to see it more clearly. So there are several blocks to define. So first is general settings. You just see here the setup file, the path to the setup file, to the TCFD setup file, the machine type. Our software provides more machines, several machines. One of them is compressor. The next are, for example, fan, pump, turbines, or water turbines. Then you define just coordinate system, so it just defined the axial of the machine axis of rotation. What I can mention, if you point to any box, you will see the help for each box. So there is a short description of each parameter. So next, in the geometry parameters, you will define the scale factor, which means the dimensions, or which defines the dimension of your input geometry. So if your input geometry STL files are in millimeters, you need to define scale factor, which corresponds. It's a multiplicator which makes from millimeters makes meters. Well, next step is the physical settings, gravitational acceleration, dynamic viscosity, reference density, reference pressure, and so on. You can define, there are predefined air and water. Then transport model, you can choose between constant transport model or Sutherland law with a given parameters, or you can change it. Then you can choose the turbulence settings, turbulence model. At this moment, we provide, or our graphical user interface provides two turbulence model, K omega SST or K epsilon. Then important part is the setup of the computation. So setup of speed lines. It means you can, let's say at one click, you can compute more speed lines, so more revolution of your rotor. So in this case, there are defined 3 speed lines with a given rotation speed. You can define it in radians per second or in revolution per minute. For each speed line, you define how many points you would like to compute or you want to compute. So for speed line 1, there will be 3 points to compute. It means it corresponds to 3 different boundary conditions. And this setup follows also speed line 2 and speed line 3. Then you should define the maximum number of iterations to compute for each point for speed line 2, speed line 3. Afterwards, you can define inlet boundary condition, and outlet boundary condition. So for this computation, at the inlet there is a total pressure, and at the outlet the fixed pressure boundary condition is imposed. Again, for each point and for each speed line, you have to define this total pressure, total temperature, and additional parameters, and the same for the outlet boundary condition. In the simulation setting part, you can distinguish between the steady state and transitional case. So our software provides both options. So this case will be computed in the steady state mode, but you can also use computation with transient. So first the steady state case is computed, and afterwards it is used as the initial condition for the transient case. Well, and the same holds for the semi-transient. It means it uses standard, let's say, stationary approach, but for the computation for the MRF, within the MRF framework, the transient solver is used. So we call it semi-transient mode. Well, then our software provides, this definition provides parallel options, of course. Here you define just how many processors want you use for computation, and here are the bounding parameters for each variable to improve robustness of the solver. Then you can choose first or second order accuracy. This averaging windows is using for averaging each variable. So at the end, you can see the average value after each 100 steps. Here you can turn on or turn off the convergence checks. So it implicitly provides some convergence criteria. So for example, at some time before the maximum number of iteration is reached, the solver can check this criterium convergence, let's say convergence check, and stop the simulation before the maximum number of iteration is reached. Bind to core is a parallel feature which can speed up the computation. For the solver, you can redefine the relaxation factors for each variable, for each equation, and of course you need to set up initial condition, initial pressure, initial velocity, and other variables. And now we are coming to one of the most important part of setting the case, and it is the setting of geometry. So the topology for the cases is that the cases consist of several components which are merged together and build one mesh, one case. So for example, you should define the rotor part and the stator part, and of course you can define other parts. So for example, in this case, component 1 corresponds to the rotor part, component 1 and component 2 and component 3 corresponds to the to the diffusers part, and the last component corresponds to the volute part. So how to define the geometry? I will start with the component 1, which is the rotor. So you have several options how to define the geometry. In our case, we are using separate STL files. Also, we can use one multi-solid STL with several components inside, or you can also use some external mesh, for example, for any software which is converted to the OpenFOAM mesh. So here you find the path to your geometry. In our case, this STL directory. In our case, case folder. And for example, for rotor part, here you simply find the rotor parts, the rotor STLs, and you pick up the type of boundary condition. So for example, there are many options: the physical inlet and outlets, communication between several patches, internal AMI, translational AMI, and rotation AMI. So sorry for small pause. I need to refresh a little bit. Well, so we can continue. Other standard boundary, physical boundaries, empty and symmetry, a general boundary wall, and then we can distinguish wall type boundaries for blade, for each part of blades, and so on and so on. So in this way you define your geometry. So here we have blade, hub, shroud, and inlet and outlet interface. So for communication between components, you use outlet or inlet interface, and by clicking on the right mouse button, you should connect it to the given component. So component 1 should be connected to component 2. And if you do it, you can directly see it in this topology sketch. So if I broke it a little bit, so for example, I connect component 1 with component 4, you can directly see it here. Yeah, so I will repair it back to the original state. And if everything is connected properly, you should see solid arrows from one component to the other component. Well, for So this is done for each component. And after that, you have to define the background mesh size. So this is the largest cell in your geometry. And you should define the internal point, so some point inside each component. You can also provide wheel diameter, but this is important just for fun machine, because for the efficiency estimation, the fun uses this wheel diameter. So for compressor this is not important parameter. Well, and that is all. What I didn't mention, for each surface, for each part of geometry, you can define minimum and maximum level of refinement. You can also add boundary layers for wall type geometry. And what I didn't say, you have two options how to connect each component. For example, the interface between rotor and stator part. Well, we use the mixing plane approach. So if this number is non-zero and positive, of course, so in this way I define 5 mixing planes between rotor outlet and stator inlet. If you would like to use AMI approach, arbitrary mesh interface, you just define 0 mixing planes. Well, so this is all basically. This is all basically, and afterwards you defined all your parameters. You have to click on apply to save these settings. So I will dock it again to my perfect, and when you type on apply, you will see your geometry topology. So component 1, component 2, component 3, and component 4. In this right panel, you directly see the setup of all parameters which uses our software. So when are you satisfied with the settings, you can go to the next step, and it is called the TCFD Manager, which is a tool for managing the computation. So just click on it, click on apply, and you see new properties box. So first you should define your directory name with your computation. So for example, my computation, I will name it. Afterwards I have to click on apply and click write case. So now the software prepare and create the OpenFOAM case for this computation. So it creates standard topology of OpenFOAM case, and when the case is saved, so now it will be done in a few seconds, and afterwards you can click on this run all button, which runs all the steps at once. So first it creates the mesh, then run calculation, and then create reports. So I can manage this by single click, or if you would like just to improve your mesh, you can click on the create mesh, then check your mesh, and if you are satisfied, you can run the calculation. So I will run all, and in each status bar you see what is happening, what is the time of the computation, what is the time of creating mesh, and in the computation part you will see also the guess of or time remaining guess. So you have the information about the end of the computation. Well, so it will take some time, so I will close it, I will stop it, and I will jump to my computed case. So I computed it today in the morning, and this is my default case. So this is OpenFOAM case with the computed case or with the results, and I can open it again implicitly there is a setup compressor file, so I can again click on it or open it in ParaView. And again, I will just click on apply. Okay, perfect. Then I will click on CFD Manager, click on apply, and if CFD Manager find already computed case, it will show the report automatically. So I can enlarge it. So anytime during the computation, I didn't say it, so also during the computation you can generate automatically this report and see what's happening during the computation. And automatically it generates the report at the end of the computation. So here we see this report. So first part consists 3 graphs, which shows the efficiency and the total pressure difference and total pressure ratio with respect to the flow rate. So you see the compressor map at in one screen. And if you would like to check each computation for each speed line, you just pick up your speed line, for example, speed line 2. And this is simulation. This is the report for speed line 2. So first part is the simulation statistics. You see what you have compute, what is the rotation speed, what was the rotation speed, how many processors you have used, and so on and so on. Information about the mesh, information about the Y+, so it's important for correct turbulence modeling, and so on and so on. On the right side, you see the flow rate, so flow rate convergence, the residual convergence for each variable for velocity, pressure, and turbulence properties. Then there is a block with efficiency of compressor. So here you see the table with the efficiency of each point. Here you see the graph and also the convergence process. So you always can check what is happening during the computation, or you can check if the computation is correctly computed. The next part is torque. So you can see the torque again, total pressure difference. It means total pressure difference between inlet and outlet. Total pressure per each interface. So for each interface, so at any position between component 1, component 2, or between each component, you see the results here. The same for the total temperature difference, and again total temperature per interfaces. And last but not least, there is a velocity magnitude per interfaces and circumferential and meridional angle. And again, here is the speed line 3 and the same simulation statistics. So you see directly the report. You can check it during the computation, and you have anytime you have this information about your computation. What I didn't mention, and I should mention, so it's an important file which you can find in the products inside the Turbomachinery CFD, and here's the Turbomachinery CFD workflow example. So a lot of information you find directly here on our web pages. And for example, what is possible to set inside the configuration file, you find at this place, so in Turbomachinery CFD configuration file, and here is the description of all parameters which our CFD software uses, and of course general notes and recommendation how to set each parameter and what it means. Here are description of meridional and circumferential angles. There is also possibility to define cylindrical background mesh, and so on and so on. So this is basic evaluation, let's say in this form. And of course, you can directly use ParaView in common way to see the result visually. So I can jump back to my case, to the computed case, and automatically our software creates this case file, which can be automatically loaded by ParaView. So if I click on it and click on apply, so I can directly see whole computational mesh and together with the results. So okay, this is the initial condition because this is time 0. So I can, for example, go to the last time step. So it means it is the last points. So we have computed 12 points. So last point corresponds to the last defined point. So third speed line and third point. And for example, here I see the distribution of the pressure. So standard evaluation you can use here. And we have also created 2 additional plugins for ParaView, which is called Meridional Average and Turbo Unwrap. So I will show you how to use this. So I have prepared, for example, I will start with Meridional Average. Perfect. So Meridional Average just makes the Meridional Average for the impeller. The how to apply it. So you just load your case by clicking on the case file. You check only internal mesh, and then I just clip out the unnecessary parts. I mean, what I do is this way. So this is at the beginning, and I just clipped out the volute, and I see only the impeller. And on the impeller, on this clip, I applied this meridional average filter. And the definition is really simple. You just define the axis and origin. So axis in the direction and origin of your axis, usually the 0 point. And you define the resolution of the raster on which you would like to see or to compute the meridional averages. So it's just a slice, and on this slice it computes meridional average of each variable. So for example, here we can see a static pressure for this impeller. So this is one nice tool to see the results for the Turbomachinery. And the second plugin is called Turbo Unwrap, which really unwrap the wheel. So it means it's like you cut the wheel in some part and unwrap it into the line, into the box. So the result is here. So again, the usage is really simple. In this way, you just open the case, and in this case, you should check the part you would like to unwrap. So for this part, it is the internal mesh, and for this this part at the bottom, it is just the blade and hub part. And anyway, you have to check this rotor hub. You have to check rotor hub part and rotor shroud part, because if I show you how to apply this turbo unwrap filter. So applying turbo unwrap filter on this case foam, and you have to define what to unwrap. So in this part, for the upper figure, you check just internal mesh, and as a hub and shroud, you have to check hub part and shroud part of the geometry. And again, you just define axis, origin, and the brake, which means the direction or the place for the cutting the wheel. And the same holds for this bottom part, but I just check for unwrapped for this unwrapping. I just checked the hub part and blades part, and on this filter I just applied the contours and I modified the legenda with the given values. So it's another tool how to create nice views on your wheel, nice views which is used for deeper evaluation of your results. What I didn't mention then on this, if you unwrap the whole internal mesh, you can make a slice. You can make a slice on it, and in this bottom part, it is the hub. Here is the shroud, and this coordinates lies between 0 and 1, which means if you cut it at coordinate 0.5, it is a halfway from shroud to hub. So this is the slice at the radial coordinates 0.5, at the relative radial coordinates 0.5. And on this slice you can show, for example, total pressure, and you can visualize the streamlines using this surface LIC filter. Well, so I think I have at the end of my presentation, of my part. So I will gladly hand my presentation to Luboš again.
Okay.
So Luboš, are you ready? I will make you
sure I am. So bring it to me. So it's the.
So Luboš, yeah, the floor is yours again.
Okay, thank you, Radek, for your remarkable live example. I will quickly finish my presentation. Yeah, I would like ask you, all the attendees, to put your questions. There is a special window, so we will gladly answer all your questions, and just take your chance. It's your time. We are here for you, so we will gladly answer your questions. So put your questions. I believe you have many questions on this workflow. Okay, so I will go on with. I will finish with how to get Turbomachinery CFD. So there's a trial version available. Anyone can try Turbomachinery CFD for 1 month to test it on your geometry. It's full version. It's unlimited. So you can do the tests before you decide to go for it or not. The paid version is perpetual, which means our clients can keep it forever and use it without any limits. So it's always perpetual, permanent. That's important. What is paid for in Turbomachinery CFD is the delivery and the technical support and maintenance, right? So when you pay for it, you pay for the delivery and for technical support, but you can keep it forever. What is important, we decided to fight hard for the universities. So universities pay only 3,000 euro per year for the support and the delivery. But of course, anybody can keep the software forever. I just repeat it to be very clear here. We believe Turbomachinery CFD is very affordable, so it's 3,000 for the universities and it's 12,000 for private industrial companies. Please contact us for more details. We are very transparent and we will gladly answer all your questions on these how to get it system. I will move in my presentation Turbomachinery CFD. Right. So I have finished my part, and now it's time for your questions and our answers. So we will take a look. Let's take a look. Yeah. So, and here's the first question. Anthony is asking us, how is the choke prediction in Turbomachinery CFD? Okay. Radek, would you like to give the answer, or would you like me to? I will. Okay, I will answer the question. So, well, the choke is a special thing, and we have been told many times by the engineers from the practice that the choke is more the system property than a single component property. So choke prediction is, it's for me, it sounds a little bit like well, nobody really knows, and yeah, so that's the answer for now. It's more the system property than the component property, and yes, we always compute the whole speed line, and especially in the end of the speed line at the low pressures, and I mean at the low flow rates. Yeah, there's the where the choke usually is, and we predict it the same way as any other commercial codes. Yes. Yeah, I would go to the next question. Yeah. Marcus is asking which boundary conditions are used between rotor and stator in Turbomachinery CFD.
Yeah, so
yes, please.
I will answer it.
Yeah, go ahead. Yeah.
So I will talk about it a little bit in more deep, let's say. So if I go to the settings part,
I'll make you a present.
Oh, sorry.
Okay,
yeah, thank you.
Now it's
perfect.
in our computer.
Perfect. So back to the settings part, and yeah, I am there. So I will enlarge it. So as I said maybe too fast. So you have two options how to set, or what, two types of boundary condition which communicates between components. So first is mixing plane approach. So it means it creates the strips with respect to the machine, so radial strips or axial strips, and you will define it here. So for example, between component 1, which is the rotor, and component 2, which is the stator. So at the outlet from the rotor, you can define any number of mixing planes. For example, I can define 10 mixing planes, and it automatically set also 10 mixing planes at the inlet to the stator, which is a neighbor of the rotor part. So for this option, mixing planes, the mixing planes number, you can change it here, or you can set the 0 value, and it means it uses arbitrary mesh interface. So just interpolation between these two parts. So this is the way how to easily change the AMI approach or mixing plane approach between interfaces. Yes, so I hope I answered the question.
Okay, thank you, Radek. Yeah, the next one, and for now it's the last one. Andrew is asking, can I design my own compressor in Turbomachinery CFD? Yeah, perhaps I'll take this.
Oh, wait, I will make you presenter. So yeah. I hope.
Okay, so I will take this question. So yeah, first of all, Turbomachinery CFD is a simulation tool. So it's CFD simulation tool, and it does no designs, right? So it's not a design tool. I can just recommend you that we, in our company in CFD support, we use CF Turbo, which is a great design tool. Maybe I can show you. I will show you what's the design tool we use in our company. So yeah. So here I believe you can see what I can see, which is CF Turbo software, which is software from German company CF Turbo, which is located in Dresden and Munich, it's great turbomachinery software, which is used for designs, for design of of all the machinery. So maybe I can show you, for example, that there are many of tutorials. I will open one compressor. I believe this compressor is exactly the compressor which was presented and simulated by Radek a minute ago. So yeah, I just briefly tell you, yeah, CF Turbo is great. Turbomachinery design software for all the machines. So we for our internal purposes use CF Turbo. It's a really great tool. You can design from the scratch, or you can load your own geometry. You can really put you can do all the details. You can design really everything. You can put all the parameters, all the everything, and that's so the machine is born here. It's designed here in CF Turbo. What's important, it can be exported directly to the Turbomachinery CFD. CF Turbo has the interface, special interface, which was developed in together with CF Turbo and CFD support, and this interface communicates directly. So my machine was designed in CF Turbo. It was exported to Turbomachinery CFD, and it can be directly taken and simulated in Turbomachinery CFD. So yeah, our recommendation is using CF Turbo for the design and using Turbomachinery CFD for CFD simulations. We are also a partner of CF Turbo, and we are also a reseller of CF Turbo products in Czech Republic, Poland, and Slovakia, but maybe it's not very important right now. So for designs, we recommend CF Turbo. And Radek, do we have any more questions, or do we have any more relevant questions? I can see, yeah, some questions on technical stuff. I mean, yeah. So we have no more questions now.
I didn't see any, yeah.
Okay.
But maybe what I didn't see, and I would like to show some comparison study because I forgot on it, and just to show.
Okay. So do I switch to you?
Perfect. Yeah, I'm here, I guess. Yeah. So just to prove that our software works, we made recently a comparison study on a compressor. So with the cooperation with ČZ Strakonice, which is a multi-branch company focused on engineering and production, and besides of other things, it is this company is a manufacturer of turbo superchargers, and we made a comparison study with cooperation with this company, and we compared the real measurements on this compressor with the impeller of size, let's say 11 centimeters in diameter. And here in this graph, you can see the total pressure ratio with respect to the mass flow rate, and the black solid lines correspond to the real measurement. The blue one is the results from our Turbomachinery CFD, and the red one is from ANSYS CFX. So you can see that our lines fitted very well the measurements. In many points, let's say in here, almost at all points, we are closer to the real measurements than CFX, for example. And yeah, so and here are the efficiency map. So again, the colors are the same. So our software is really robust and is comparable, and in many ways it's almost better than any other commercial software. So yeah, so it is not only the empty words that this is some turbomachinery, but it really works, and it's robust and really useful. So yeah, that's all what I
Okay.
like to say and mention.
Okay, thank you, Radek. And we have one more question from Stefan. He asks, can we see the mesh, please? So would you
Oh,
be so kind to show the mesh of the tutorial?
Okay, so here I have this case, and I will just show this solid, and okay, here is our surface mesh. So for this tutorial purposes, we made a rough mesh to compute to get the results in short period of time. And so yeah, this is how it looks. I can make, for example, slice. So it uses again, okay, surface with edges. And for example, I can use this crinkle clip, okay, to see really the mesh. So I didn't mention it. So mesh is created using SnappyHex mesh, which is fitted with our best practice parameters, and we are commonly use it. And for example, also this.
Radek, sorry to interrupt. Can you minimize your window of the GoToWebinar because it's white screen? I don't know why it's white rectangle. Yeah.
There's black. Okay.
Yeah.
Thank you, Bosch.
Thanks. Sorry for interrupting. Just go ahead.
It's okay. Thank you for the note. And yeah, what I said is based on the made by SnappyHex mesh with our best practice setup. And what I would like to mention also, this results was generated using the SnappyHex mesh, so we have good experience with Snappy, and this is robust, really robust for automatical meshing of almost any type of geometries. So I hope I answered the question.
Yeah. It's the SnappyHex mesh what we use. It's highly automated. It's highly it's great tool for very complex geometries, and it's very robust in terms of which machine you do the mesh, and also the results are perfectly the same results as any hexahedral mesh. It's also hexahedral dominant mesh. Like 90% of cells are hexahedrals. So we have really great experiences with SnappyHex mesh. Yeah, that's from me.
Yeah, thank you, Bosch.
Yeah. So I think this was the last question I see. Maybe I will just briefly check the email. Sometimes people write a question to our email. Nope, no questions at the email. So we will closely conclude. So yeah, I will take the word. Or I will take it.
Okay.
Yeah. Okay. So I believe we are now in the in the we are in the end of today's webinar. So we would like to thank you for your attention. Thank you very much. Yes, we will. Yeah. Thank you for your attention. Thank you for your time. We believe we give you some information, some relevant information about Turbomachinery CFD. We believe it's great software. We believe we are creating something big. It's still developing. There are new features coming, and so we believe we are creating the best CFD software for Turbomachinery, which is available in the market, and we are ready to prove you. So feel free to contact us for the details. We are very transparent. We tell you all the details about it, and yeah, I think this is it. Yeah. So thank you. Okay.
Unfortunately.
Yeah. Everything.
I hope see you next time.
Yeah.
And
okay. So thank you for your time, and yeah, bye.